So, yeah, we will be continuing with convex sets and convex functions. So, one of the interesting example is norms. Okay, x functions, and we can recall what is a norm. Okay, so f from Rd to R is a norm if it satisfies the following. So, first let us see what are the properties. So, f x is greater than equal to 0 and f x equals to 0 if and only if x equals to 0. Okay, that is the first property. Second property is f of lambda x is mod lambda f x. Okay, so that is where lambda is a scalar. And then third property is the triangle inequality. So, f of x plus y is less than equal to f x plus f y. Okay. So, yeah, so there are names for this. So, this is called definiteness. Then second one is called positive homogeneity. And the third one is called subadditivity. Okay. So, this function is called a norm. Okay. So, such a function is called a norm. Okay. And we usually denote norms by this denote by these two parallel lines and then whatever the argument could be. Okay. Okay. So, norms are also convex. Okay. They are convex functions. Okay. So, norms are okay, norms are convex functions. So, it just follows from here. Okay. There is no big thing here. Okay. So, to prove this would be very easy. Okay. So, basically if you recall definition of convexity of a function, then it's the line should be above. Okay. So, basically theta f x plus 1 minus theta f y, it should be above. The line joining 2 points on a function should be above the function values. Okay. And this should be true for all x y in domain of f. Okay. So, basically this is what we are supposed to prove. So, we can essentially start from the right hand side because subadditivity is like less than equal. So, it makes sense to start from here. Okay. So, let us use the usual notation for the norm. Okay. So, in this case the function is the norm. So, norm of theta x plus 1 minus theta y. Okay. And this comes directly. So, this is of the form x plus y. So, that we apply subadditivity here. So, this is theta x plus 1 minus theta y, and then we apply positive homogeneity. Yeah. So, what will come out will be mod of theta. Theta is anyway between 0 and 1. So, that is already positive. So, we do not have to put a mod here when theta comes out. So, this is theta mod x plus 1 minus theta norm y. Okay. So, but that is exactly what convexity means, right. So, this implies that the norm is a convex function. Okay. Is a convex function. Okay. We have not been very specific with which norm. It is like any norm. Okay. Now, you put 2 norm, p norm or any norm. Okay. This is just a notation. Okay. So, any norm must be convex function. Okay. Then we can also define some specific norms. So let us say two norm. So let us say some vector norms. So one of the most popular is something called L2 norm. So L2 norm here is denoted by sub 2 here. Okay. So in this case we will write this as x, okay, and this is square root of x1 square, x2 square, okay, I mean square root. Okay. So this is the 2 norm, but you can generalize this. So you replace 2 by p, okay, and since p could be odd, so to prevent that maybe put a mod here and then put a p here and then 1 by p, the pth root. Okay. So in general we can define a very generic p norm. Okay. So if we do that, so let us say if we do that, then okay, so we will put a mod here, right? So plus x2 plus xn p and 1 over p. So this is called p norm. Okay. So in general you can put any p you want. Okay. So this is called p norm. And then there are some special ones like infinity norm. So infinity norm is just the max of the entries. So max of mod of xi, where I equal 1 to n. So basically you take the vector x and take out the maximum entry of the vector x. Okay, so that's the max. And then there is something called Frobenius norm. So Frobenius norm is applied on matrix. So Frobenius norm is for matrix. Okay, Frobenius norm. So let A be complex n by n matrix. Okay, then the Frobenius norm of A is denoted by this. This is essentially Euclidean norm, just that I will flatten the matrix. Okay, so row and then another row and make it a vector, and then do the 2 norm. Okay, so that will be the same. Okay, so basically this is square root of sum of mod of Aij. Okay, I mean mod was not required, I guess, because there is already a square. So Ij. So basically what I did is I took all the entries of the matrix and I squared them and took a square root. It's the same thing as saying like make the matrix as a vector and do the 2 norm, right? So there is some interesting relationship of the mod of the Frobenius norm with the trace of a matrix. So Frobenius norm of the matrix A is square root of trace of A transpose A. Okay, but yeah, I mean if you see the trace of A transpose A, then in A transpose A, because trace is a sum of the diagonal entries, so you will see when you do A transpose A, all these entries will show up. Aij squared, okay. So all these entries will show up only on the diagonal, and hence you will take a trace, then it will be the sum of the diagonal entries. So this will exactly this. So this quantity it will exactly be trace, and then you will be taking square root here as like you did here. Okay, so that's a simple thing to check. So in general I can define some other matrix norm. So this is a Frobenius norm, but we can define matrix norm as follows. So let A be m by n and this be any norm. Okay, so then we can define a induced norm. The norm is induced from this, so we can define an induced norm which is like this: is supremum of x not equal to 0 norm of Ax by norm of x. Okay. So this is called induced matrix norm, and one can prove that this is this is a norm. Okay. So basically it has to satisfy the definiteness. In other words, if yeah, if this norm is 0, then A must be 0. Okay. And in general it should be greater than equal to 0. So that makes sense because on the numerator and denominator both are positive and x is non-zero, so denominator cannot be 0, so hence it will be positive for sure. Okay. And yeah, the one thing is this thing is like if fx is 0, meaning norm of A is 0, then it's necessarily A must be 0. Okay. So this has to be shown. And f of lambda x, so meaning I will put lambda norm of lambda of A, then essentially lambda should come out and it should be norm of A. Okay. So that seems like okay to me, because the lambda does come out and I am left with norm of A, and then this is the sub additivity. Okay. So more or less all the things seem okay. So if this is indeed greater than or equal to 0, because this is greater than equal to 0, so indeed norm of A is greater than equal to 0, because norm of Ax, this being a norm, is greater than equal to 0, and norm of x is greater than equal to 0. Now norm of A going to 0, why should it imply then that A must be 0? Right? So this is this part, right? So can we prove this here, right? So if norm of A is 0, so norm of A is 0, then what should this imply, right? Should it necessarily imply that A must be 0, right? So our claim is that if norm of A is 0, then this should necessarily imply that A is 0, right? So do you see this in this case, right? If I put norm A equal to 0, if norm A is 0, then what I get is this supremum thing is equal to 0, and then from there I must derive that A must be 0, right? So do we see this? So if norm of A is 0, then supremum of this, okay, so let's see. So supremum of x not equal to 0, norm of Ax by norm of x is 0. Can you conclude from already from here itself, like the minimum of this is 0, right? And we are saying it's equal to 0, right? So it must be 0. Right? We already proved that this must be greater than equal to 0, right? Because both are positive quantities. So must be greater than equal to 0, that is known. And now I am saying that it's equal to 0, right? So what does this say about this? This equal to 0, right? So we know that this is greater than equal to 0, and now we are saying equal to 0. So the only possibility for this quantity is that this must be 0, right? Now from there, what do I conclude, right? So this guy is 0 by, so this implies what? Implies norm Ax is 0, right? So norm of Ax is 0, norm of x is 0 means Ax is 0, right? So if norm of x is 0, then this implies what? Ax is 0, but that may not necessarily imply A is 0, right? Which is what we wanted, right? We wanted A 0, right? But x may be non-zero, but still A being non-zero, I can have Ax equals to 0, right? But my goal was to prove that A equals to 0, right? Yeah, x cannot be equal to 0, but still we cannot conclude that A is 0, right? Because A may be a singular matrix that takes non-zero to 0, right? So A 0 means like it's all entries are 0, right? So somewhere we need some more argument, right? I mean, one thing I have dropped here was that this should be there as well. Okay, I'm saying that this quantity is greater than equal to 0 and equal to 0, right? So this quantity, not just this, right? So this is this quantity. Okay, maybe this was the term we are missing, right? So from here onwards, can I claim? Okay, so certainly, so this is something until here it's fine, because this is something I can conclude, because this guy was greater than equal to 0, and this A norm A being 0 was the hypothesis. So until here is 0 is fine. Okay, from here onward we are supposed to prove that this should necessarily imply that
it's true for all x, right?
this is true for all x.
Like supremum of a term that's always greater than equal to 0 is 0. It implies every term is 0 for all x. So ax is 0 for all x. A has to be 0.
Yeah, Ax is 0 for all x, right? Okay, so because this is 0 for all x. Okay, that's what we have. Okay, right, because this is being done for all x. Okay, so this necessarily implies that this is norm of Ax is 0 for all x. Okay, so not just supremum, but it's like all x. But if that is the case, then the matrix must be 0 itself. Okay, this essentially implies that Ax equals to 0 for all x. Okay, now we can say that A must be 0. Okay, if it is 0 for all x, then we can certainly say, if it was just 1x, then we cannot say, but it is for 0 for all x, then we can say. Why is that? So which x you are supposed to choose, which will force me to prove that all A must be 0, right? Okay, can I? So what is the meaning of matrix multiplication, right? What does it take out from the matrix, right? I mean the view of matrix multiplication, right? A times x, I see it as transformation, but some linear combination form is a linear combination of columns. Okay, this view is much more important than inner product view. Okay, because matrix multiplication is a linear combination of columns. So if I write this as A1, A2, so these are my columns. Okay, and then I have x1, x2, xn. Okay, so matrix times vector, in a column view, it's same thing as x1 column A1 plus x2 column A2 plus xn column an is 0, right? So this is another way to view. Now I'm saying that I'm allowed to pick any x I want, right? So I will pick now x in a way that it will force first column to be 0, second column to be 0, because I'm allowed to do that, despite keeping x non-zero. How is that? I will keep the first component 1 and second component 0. This forces A1 to be 0, right? Right. So I have possibility because I am allowed all x. So basically, you feed in the canonical basis vectors 1 0 0 0 1 0, and that way it spits out A1 equal to 0, A2 equal to 0, and then everything is 0, right? So choose vectors x to be of the form 1 0 0. Then this implies first column is 0, and then you choose x to be 0 1 0, then this is by second column equal to 0, and so on. Okay, so that's why Ax equals to 0 for all x means necessarily that whole matrix must be 0, right? Okay, so now we did the first one. Second one is simpler because lambda comes out on the right hand side as well, because that's a norm anyway, so we can do it here. So what we are saying is lambda x. So this is lambda a. This is our lambda a, and so this is for now lambda a. So in there also we will put lambda a. So supremum of lambda a x. So this is supremum over x. This is supremum over x. Now obviously this being a norm, lambda does come out. That's why we call it induced norm, because there is already a norm, valid norm. We are inducing it. We have a norm which is meant for a vector, and because this is ax is a vector, so I have some valid vector norm, and using that vector norm I am inducing a matrix norm, and that's why it's called induced norm. Okay, so this being a norm, obviously lambda will come out. So lambda comes out ax by norm x, and obviously lambda also comes out of the supremum because it does not have anything to do with x. So supremum ax by norm x, but this is exactly lambda of norm of a. So this is what we wanted to prove. This is mod, so we can put mod also, it's fine, because the same mod comes from this norm. So this is mod, right? And then third one is also fine, because the inner one will be, it's like a plus b now, two matrices, and then because this is a norm, so ax plus bx, the two vectors, and then sub additivity for two vectors, and then supremum splits. So that's also trivial. Okay, so so we can do it here. This is just one line. So here we are saying sub additivity for this. So this is supremum over x, and then this is a plus b x by norm x. So but then this is supremum over x, and this is like less than equal to, I can already write. So this is norm ax plus norm bx, because these guys are a norm, and then we can split the supremum, and so this is equal to norm of ax by norm x plus norm of bx by norm x. Okay, and supremum also. So essentially we have proved this as well. So this is supremum over x. Supremum gets split here, supremum over x. So this is norm a plus norm b. Okay, so this is good, because this induced norm is very useful, because often you work with matrices and sometimes even tensors. So these higher norms on these matrices, tensors are quite useful. Okay, so if we choose some certain choice of a norm, let's say 2 norm, then it's a little bit interesting, because if I change this norm to a 2 norm, then it is essentially exactly equal to largest singular value of the matrix A. Okay, so that's an interesting result for a special case of 2 norm, in matrix norm induced by 2 norm. Okay, so it's good to note that. So essentially what this is trying to say, an interpretation of this is, norm of a matrix measures how big or small it is, right? So the matrix will be big or small in the sense that I apply some test vectors x on the matrix A, and I see how much stretching it can do relative to x. And if it stretches more, then we say that the matrix has higher norm. Okay, if it stretches much less, then it will be small. And so that's how we kind of measure length of a matrix in some sense. Okay, so so the special case, as I said, will be the two norm. Okay, so let A be any matrix, then its operator norm is given by 2 norm of A is supremum. It's the same definition, but just that the norm is now 2 norm. Okay, there it was any norm. Okay, so those results are any norm. Here it's more specific. Okay, so it turns out that this guy Now it does make sense, because if you see which is the vector that will create the maximum stretching, right? When I apply A to some vector, which is the vector that will get relatively maximum stretched? It must be an eigenvector. Okay, the largest eigenvector, because we are looking for supremum, so it should be the largest eigenvector, because A times some vector u is lambda u, u being an eigenvector. I know that for largest lambda, okay, for the corresponding u, I can stretch the maximum. That is the maximum I can stretch relative to u. Okay, relative to u, this is the maximum. So that that is the reason why this will be the lambda max. This is lambda max if A is symmetric. Okay, otherwise it's singular value. Okay, because for symmetric matrix we have real eigenvalues ensured. Okay, and there we can talk about largest or smallest, but if non-symmetric, then even it could be complex number and we don't know the ordering also. Okay, but for non-symmetric there is always singular value. Singular values are always positive again, so again I can do the ordering for singular values. Okay, so in general you don't have any problem here, in the sense that even if it's non-symmetric, A times x is some vector, and 2 norm is some number divided by some number, it will be some number. Okay, so in the A non-symmetric case it will be singular value, that's fine, but in the case when it's symmetric, it turns out that it will be lambda max. Okay, so so this, if A is symmetric, okay, so but in general for non-symmetric we can define it to be sigma max. Okay, so we have norm, and we have something called dual norm. So let me define something called dual norm. So dual norm, so dual norm is defined. So let this be a norm in RD, then its dual norm denoted by star is defined as supremum of U transpose X given norm X is 1, or it's like less than equal to 1, So dual norms are defined like that, and one can check that dual norm is also a norm. Okay, so check that this is a norm as well. In general, we have one result that if 1 by p plus 1 by q is equal to 1, okay, and if we have some p, okay, let's say it's a p norm, so this is a p norm, right? This is a p norm. Then one question could be, what is the dual of a p norm? It turns out the dual of a p norm will be q, where q satisfies this. Okay, then its dual is p norm, q norm. The dual of a p norm is q norm, but that q should be such that it satisfies this. So 1 by p plus 1 by q must be 1. Then p norm is a dual of a q norm. Okay, so for instance, let us say 2 norm, right? What is the dual of a 2 norm? 2 norm itself, right? Because 2 norm p is 2, then I am looking for q, for which 1 by 2 plus 1 by q is 1. So if I choose q to be also 2, then 1 by 2 plus 1 by 2 is 1. Okay. So, dual of a 2 norm is 2 norm itself. Okay. So, let us see and write this here. Dual of a 2 norm is 2 norm itself, right. So, example, dual of 2 norm is 2 norm itself, okay, is 2 norm itself, okay, because in this case 1 by 2 plus 1 by 2 is 1. This is our P and this is our Q. So, this was not very interesting. Dual of 2 norm is 2 norm itself, and maybe we can try something else. Let us say 1 norm. Dual of a 1 norm is dual of 1 norm is, we have to check this, right. So, what we got is 1 by P plus 1 by Q must be 1. So, now we solve for Q here, and that will be the dual. Okay. So, what is Q here? Infinity. Okay. So, it seems like dual of 1 norm is infinity, Q is infinity, is the infinity norm. Okay. And it is also the other way. If it infinity norm is given, then the dual must be 1 norm. Okay. So, it is a symmetric. Okay. So, this way, like, we can have dual. Duals are used in optimization methods at some point. Okay. So, we are building some skills. So, in this chapter on convex functions, this is all we are supposed to do. We taken a norm, we have shown variety of norms, we have shown that norms are in general convex, then we went for norm induced matrix norms, and that also is a norm obviously, and then we looked into special cases of 2 norm. In this case, it turns out that this is lambda max or sigma max, and then we have defined a dual norm, and dual norm certain dual norm obviously itself is a norm. Those things can be checked. So, this is kind of the wrap up of convex functions, we can say. I mean, not a complete wrap up, because we also need to study, let us say, conjugate, which is also a convex function. So, regardless of what f is, conjugate is convex. So, it could be included there, but okay. So, let us, I can maybe leave an open problem for you, and any of you can solve this. You can write a paper. So, open problem. The function defined to be f(x) is 1 to the x plus 2 to the x plus dot 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 plus n plus 1 to the x divided by 1 to the x plus 2 to the x plus dot 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 plus n to the x. The difference seems to be n plus 1 to the x, n to the x. Until here it seems the same, is log convex. So, basically you take a log of this, and that should be convex. Okay. So, maybe I didn't define log convex. So, what it says is like log of f(x) is convex. That is what you are supposed to prove. So, is log convex that is what you are supposed to prove, is that a log of f(x) is convex. Okay. So, you know convex functions, right. You know definition of convex function, you have seen some examples of that. This is an open problem. Okay. Yeah, there are a few more, but yeah, let us go ahead and let us look into something called conjugates. Okay. So, what I will define is something called conjugate or Fensel conjugate. So, Fensel conjugate is defined to be like this. So, f star given f(x), I define f star y, which is a conjugate, as supremum of x in domain of f, and then x y minus f(x). Okay. So, this is called conjugate of f(x). Okay. Given an f(x), I can consider a conjugate, and So what is interesting here to note is that f star, meaning the conjugate f star y, is a convex function in y, regardless of f is convex or not. And why is that? Because it's a supremum. Supremum of, as a function of y, it's linear. Okay, as a function of y, this is linear. So this is because it's x transpose y, right? So here y appears only here, and this x transpose y. So as a function of y, it's a linear function. So linear function of y, and linear function is necessarily convex, right? So this implies convex in y, and we have done a previous result that maxima of convex functions is convex. In other words, suprema, which is like a maxima. So supremum of convex functions is convex. Okay, so this is a set of supremum of convex functions over x. So this implies that this is convex. Okay, so this implies f star y being supremum of convex functions is convex. Okay, so remember last time I showed you why is that. So I have drawn couple of convex functions like that, and I said supremum, so meaning I take the maximum. So so let's say this until here is this, and then after that is this. So indeed supremum of a convex function is convex. Okay, so we know this, and that's we used. So what is interesting here is that the given function may not be convex, but the conjugate is. So sometimes you may want to work with conjugate. In particular, if you form a dual of your problem, then this f star somehow comes up. Okay, when forming a dual form. So we will see what a dual form is, but yeah. So this is interesting, and because we like convex functions. Okay, because convex functions have unique local minima because they are ball shaped, so they have necessarily unique local minima. So it's always easier to work with convex functions. We can prove results that guarantee of convergence and all this can be done for convex functions. Okay, so here obviously we would like to know, although we have defined this, but we want to know how is it actually computed, right? So what could be the closed form solution of f star y given fx, right? We have to somehow do this supremum thing, right? So we may have to kind of see one example in case. So let us say we have some example on this. Yeah, so let us see an example how to compute conjugate. So let us say I'm given a function fx is ax plus b, then the question is find f star y. So if you write down f star y is supremum of, obviously supremum over x of inner product of x with y. Okay, so this remains the same, it's inner product of x with y minus fx. So fx in this case is ax plus b, so it's minus of ax plus b. So we are supposed to find supremum of this guy, right? This is like y transpose x. So I mean this is a scalar valued, so we don't, I mean inner product is just xy. Okay, this is like xy minus ax minus b. Okay, so let us simplify a little bit. So this is supremum over x of yx minus ax minus b. Okay, so remember that x and y are scalars, x, y are scalars, that is real. Okay, real, or it could be complex also, it doesn't matter. In this case it's real. Okay, so what we are supposed to find is supremum of this guy for a fixed y, because this is a function, so I will put in one fixed y and then say what is the output, give me the output. So you can imagine that y is fixed, so fixed y, now maximize this as much as possible, right? And obviously since this is a valid function for a fixed y, I want a fixed finite value. If it blows up to infinity, that's not a valid value. So what you are supposed to do is for which values of y you will get a finite output. that will define a valued function, right? Okay. So that's from there itself you know how to compute. Okay. So for instance, let us say I fixed y to be, let's say, y1. Okay. So let us say for I fixed y1. Okay. So this got fixed. Now I am asking for, is there a supremum of this which is bounded? Okay. So and this is supremum is over x, right? So I can simplify this as y1 minus a x minus b, and this is the supremum over x, right? So this is a linear function in x, right? So linear function in x when it is bounded, that's the fundamental question now, right? When it is, yeah, then y1 equal to a, right? If not, then what will happen? It can lead to infinity because of the x, right? Because whatever constant I have, if it is non-zero, then there will be a x, whether it's negative or positive, it doesn't matter. Okay, either way I can move it to minus infinity or plus infinity, right? So as long as this guy is non-zero, the fact that I'm allowed x to be anything, so if it is something positive, then I take x very large, it goes to plus infinity. Okay, because b is some finite number, so b will be overtaken at some point. Okay, however big it is, b can be overtaken and this could be made infinity. Okay, or it could be negative infinity also, it doesn't matter. But the point here is that linear functions are by nature, it can go up to infinity or minus infinity. The only linear function that is bounded is constant or 0. Okay, the constant basically. Okay, so in this case our only possibility is when y happens to be a. For y anything else, so what I'm saying is, like, I'm fixing y, but then from my analysis I find out that the only possible good value for y is a, for which I get some finite value which is minus b, and for anything else is going to not work. Okay, it's going to give me undefined values. So function giving infinity is called undefined, right? Unless we work in extended real valued system, there is analysis people do with extended real value system where plus minus infinity is allowed, but in this case no. Okay, so in this case we only deal with finite values and then define function to be valid in that way. So so from there we get that, right? So so this implies, so here y1 minus a x minus b is bounded only when y1 is a, right? So only domain, valid domain of your dual is a. Okay, domain of the dual f star is a, so meaning domain of the f star is necessarily a. Okay, just one entry in the domain, and for this value we have the output defined to be minus b. Okay, so hence we define our dual function to be f star a is minus b. Okay, or that's it, f star a is minus b. I don't have to do anything. Okay, it's defined only on a, so that's it. So obviously this is a constant. So this is also like convex. Okay, constant functions are convex. So dual necessarily has to be convex. We already proved that, and one can again check this here. So you can play around with some more examples. I won't do that. Okay, so you may play around a little bit more. There is a way to see Fensel as a convolution, but I will keep it for later when we will go to some fixed point iterations, non-expansive maps, and so on, proximal methods. So those things use these things, but for the moment it will be a little bit too much right now to do this. But what I want to go for now is subdifferential. So these are the new things essentially for those who have not seen non-smooth optimization methods. So we will enter into that. So non-smooth means non-differentiable. Basically derivative doesn't exist. Then we will define something called subdifferential. Okay, so if we look into differentiable functions, right? So if f is is differentiable, then this means that at any point x I can compute the derivative and it's unique, right? So then this implies that at any x in domain of f, there exists a number let us say g such that f prime x is g. Okay, the slope of the is g. Okay, and not just that, and this g is unique. Okay, so there exists unique. Okay, so in math sometimes they do this. There exists an exclamation means unique. Okay, so there is a unique g. So meaning there is a unique derivative at that point. Okay, then we call a function to be differentiable. Okay, so examples are x square. So this has derivative at all the points, meaning here the derivative of fx is 2x at any x. Okay, but the non-example is fx is mod x. Okay, so fx is mod x does not have unique slope at all the points. So where does it does not have a unique slope? At which point? Okay, at which point? 0, right? At 0 it doesn't have, right? So meaning here this point, right? Because here at each point less than 0, for x less than 0, I know that this is kind of like negative. So fx is minus x. So here I can take derivative. So fx is minus 1. So until this point less than 0, I know that the slope is negative. I can say the same thing for the positive x greater than 0, then fx is x, and in that case also I can take derivative, it's 1. So here also it's well defined. The only problem is at x equals to 0. X equals to 0, there are multiple slopes for this, right? And, so it could be obviously this line itself is a slope. Okay, but then this is also a slope, this is also a slope. Okay, so basically you have multiple slopes. So how many slopes you can have? All possible slopes going from here to here. So meaning here at 0, at x equals to 0, there is no unique slope or tangent of fx. There is no unique tangent for fx, hence f cannot be considered differentiable. At x equal to 0, it's not differentiable. Okay, so hence fx at x equals to 0 is not differentiable. Okay, but somehow, I mean, having functions like this is quite common. Okay, so if you do deep learning, then you have functions like ReLU, okay, which is non-differentiable. ReLU is like not, I mean, yeah, it's like this. Okay, so it's non-differentiable here. Okay, so we will at some point, like I will introduce this neural network basics also maybe, but these are the components used in ReLU, I mean in deep learning, deep neural networks as an activation functions. And here, since these are used there in the loss function, we will have this. We have to do optimization on this. So there will be a problem of how to find a minima on those kind of functions, right? So here also there is a problem that there are many, because as soon as you have a corner, you have multiple ways to find a tangent. Okay, so these are all tangents to the curve. Okay, so in this case, the slope at these values will be all possible values from here to here. Okay, now coming back here, in this case, at x equals to 0, it's not differentiable, but then people have generalized this and saying that okay, it's not differentiable, you have many possible values, take all those values as the slope of the function. In this case, values ranging from -1 to 1, they are all considered slopes at 0. Okay, so it's not differentiable. So take subdifferential basically. I will define properly subdifferential, but subgradient. Okay, so this is a new term that that was introduced. So I can usually take gradient, but then in cases where I cannot, I define something called subgradient, sometimes also called subdifferential, and that means that at certain points it will be a set of tangents, okay, rather than having unit tangent. So the notation to use this is del f x computed at x equals to 0 is a set minus 1 1. In this case, an interval between minus 1 and 1. Okay. So these things will be used somehow in the algorithm, because so why are we interested in gradients, right? The gradients we are interested because they are useful in minimizing a function, right? For example, via gradient descent method. So we will see algorithms a bit later. So being able to compute gradients is an essential requirement in optimization method, and places where it's not differentiable, we can go with this subdifferential. Okay. So when we define subdifferential, then how can we work with subdifferential, right? So this is one of the questions, and then there are topics like subdifferential calculus. So, okay, so we can get a more intuition behind this. But first, I will properly define subgradient. Okay, so subgradient definition actually comes from some intuition that we had for the convex function, basically. Okay, so for the convex function, if you remember, we had something like this, and we said that for a convex function, at any point, I have the tangent that I draw at any point of a convex function. The tangent values are the lower bound. Okay, so this is my tangent. So tangent is supposed to be a lower bound for the convex function at any point I take. So for instance, here the snapshot, the tangent values are smaller than the function values. So we wrote this inequality: fy is greater than or equal to fx grad f times y minus x, right? So this is exactly what characterizes convex functions. But then this can give you an intuition, right? Because for a differentiable function, there is a unique tangent slope, right? But if it was a corner point, you can extend this definition, right? You can say that, okay, take all the corner points, right? So the grad f term that appears in this, the slope of this, you generalize that itself. So you say that what are all possible vector not apart from grad f. Okay, apart, like it's not possible at the corner, we cannot say grad f, but it's like all possible vectors that you can define as a slope for which fy values will be higher. Okay. Okay, so the intuition is coming from convex sets. So I'm going to define subgradients with the intuition from here. So so remember, this was our fy plus grad fy and y minus x. So remember, this is the line equation of this tangent. Okay, and what we say is that fx at any point fx is always greater than or equal to the point on the line. Okay, so this was the convexity definition. A function is convex, a differentiable function is convex if fx is greater than or equal to fy. So recall from the first class is fx is greater than or equal to fy, right? Fy plus inner product of grad f y minus x, or x minus y. Okay, so there is a flip here. Okay, so it should be x minus y. So this is true for all x and y in domain of f. Then this implies f is convex. So this is something we have done in the last class. If f is differentiable, and if we have this inequality fx greater than or equal to fy grad fy x minus y for all x and y, then it necessarily characterizes convexity, okay, for a given function f. But our intuition for subdifferential comes exactly from here. Here I had a unique grad f. Now I will change this. I will say find out all possible g. So this was my one slope, grad fy. Now I say all possible g for which this will hold, fx will be greater than. So this will be all valid kind of lower bound in that point. Okay. So so the intuition comes from here. So let me draw another picture, and from there you can relate to what I am saying. So we can have, I mean, this kind of functions are nice because they are differentiable and so on, but the reason why we are studying subdifferential is that we can have situations like that. Okay, so this is like non-differentiable because there is a kink here. Okay, so basically corner. So these are the points where the function is not differentiable. Okay, and we want to find a valid definition of a subgradient via that. Okay, so that's fine because, as I said, what I will do is that I will instead of grad f, I will keep a generic g kind of thing. Okay, so fy plus put a g here. So this is like one specific g. I got one tangent, so g1 x minus y. But then I could have drawn something else also, like this. So this will be another tangent. So fy plus some g2 and x minus y. Okay. Similarly, we can do something else. This will be for g3. So these are lines with different slopes, and this essentially characterizes all the slopes that you could have at that point. Okay. So that makes sense. Okay. So in this case, it's like fx for all the g for which fx is greater than or equal to fy plus g x minus y. Okay. So find all such g for which this happens. Okay. Any questions? Any doubt here? Okay. We will collect all those slopes. Okay. For which, I mean, the only thing you have to ensure is that this remains below for it to be a valid tangent. Okay. And what is interesting here is that it does not have to be maybe globally also. Okay. So because subgradients is a local property, right? Okay. So if f is convex and differentiable, then grad fi y is the unique. If we remain at the convex, let's say, okay, maybe I have to maybe correct a little bit. If f is convex and differentiable, it's unique g. Okay. But if f is convex and non-smooth, like here, okay, and if f remains convex, like it is still a ball shaped, okay, ball shaped, but like kind of like this, but non-differentiable, then obviously all those g's that I will take has to be this for all x and y. Okay. Okay, let us stick to convex for the moment. Okay. So this is still convex, so this should be true for all x and y, because any of these tangent must be a lower bound for all the function. Okay. So I may not have to ensure it locally because in general the function can be non-convex also, right, but non-smooth. Okay. Okay, like this, right? So it may happen like that, but then here defining this for all x and y or globally won't work because this guy crosses this, right? Okay, so there is no longer a true, right? Because there is a slope here, but globally this slope is function value is below at some point than the point on the line. Okay. So in general, if we say that for non-convex, if we have to define non-convex for subdifferential for non-convex, we have to do it locally. Okay. There exists a neighborhood where, okay, there exists a neighborhood because at neighborhood at least there will be at least at this point. For those values, it will be a lower bound. Okay. So we have to be a little bit careful when we define subdifferential in general for non-convex. But if we retain convexity, then obviously any of these slope, okay, we want it to be a lower bound for the whole everywhere, okay. So if we fix to convex, then subdifferentials are the values g slopes basically for which they remain a lower bound for the function values. That's what it means. Fx is greater than or equal to Fy. So this Fx is the function value, and this is the function this is the value on the line which is passing through Fy and so on, and this is true for all x and y, okay. So then for convex non-differentiable, what I'm trying to say is for convex non-differentiable this is good. For non-convex I have to be a little bit careful. There is no guarantee that any tangent becomes a lower bound globally for a non-convex function. That's not possible. In fact, that is exactly the reason why it's non-convex. Well, no, sorry. I mean, it may not be. Like, it depends on the point, right? I mean, basically, there may be a point. I mean, what I'm trying to say is it necessary and sufficient, right? So, if it does not get satisfied, does it necessarily imply non-convexity, right? So in general, what we know is that for non-convex, any tangent drawn to a function may not be a global lower bound, okay. So to summarize a little bit of what we have done with the gradient and subgradient. So if the function is convex and differentiable, there is unique gradient, okay. So if f convex and differentiable, then grad Fy is unique. Now, since subgradient is a generic term, I can call grad f also as a subgradient. It's just that in this case it's 1, okay. So it's a unique subgradient. At the point y. Yeah. So a vector g is a subgradient of at a point y if and only if Fy plus g x minus y is globally smaller than Fx, okay. In general, for convex non-differentiable function, this is the definition of subgradient, okay. It is globally also smaller than Fx. Determining all subgradients at a point in general may be difficult, okay. So in general, determining all subgradients is determining all subgradients is difficult. Difficult in the sense that if you look at the definition, for a given vector g, you have to kind of make it validate this for all x and y, which may not be easy to check all the time. If the convexity is relaxed, then things become very wild for subgradient also, specifically for subgradient. So in general, chain rule works. A chain rule of the derivative that we have, the usual derivative that we have, we can apply chain rule, and similar chain rule we can apply for subgradient. But if it's non-convex, it doesn't work, okay. So for without convexity, things become wild, okay. So one has to be a little bit careful there. For instance, chain rule doesn't work, okay. So chain rule does not work. If we look into a very specific example where max functions are usually not differentiable, so if we look into some example, let us say fx is max of f1x f2x, let us say max of two functions, and both of them are convex. So f1 is convex, f2 is convex, and individually they are differentiable, but the max function that comes out may not be differentiable, okay, after the max, okay. And that makes sense because we, again geometrically we have seen this is one convex, this is another convex. So the max guy is this and then this. So there is a corner here, okay, like this and this. So there is certainly a corner here. So this is not differentiable in the usual sense. So one can have a subdifferential. So what is the subdifferential of max function, right? So that's something we have to check. Now it depends on which one was bigger where, okay. So if this guy was bigger, then it will take the derivative of this, and if at certain points this guy was bigger, it will take the places where it's differentiable, it will take those, and places where they intersect, which is this case where f1x is equal to f2x, f2x. So let us say this point where they mix, they intersect, that's where the subdifferentiable non-smoothness will come, non-differentiability will come, because otherwise individually they are differentiable. So individually until here it's differentiable, this guy is differentiable. So only kink here happens to be when f1x is f2x, okay. But in that case, so until here we can define, and here we will define what was found until here and what was found until here as a subdifferential, okay. So let us write this down. So fx1, so if fx1 is greater than, I mean f1x is greater than f2x, then we have unique subgradient of f, and in this case it's because f1 is greater than, it's a max function, so it's f1 prime x. So that's fine. And then the other way is like f1x is less than f2x, then in this case obviously unit subgradient of f2 prime x. And then interesting case is when f1 y is equal to f2 y, that's when they intersect. And in this case it's no longer unique, but it has to be between f1 prime y and f2 prime y, okay. So this is between subgradient is the interval f1 prime y and f2 prime y. Individually I can compute f1 prime y because f1 itself is differentiable, so it's fine, it's a valid. So at y derivative of, okay, so it can be made a little bit clear. Let us see what is happening. So let's see this and then this. So basically until here, right, this is our y, let us say. So y until here, right. So at y I can certainly compute for f1 and f2. So this guy until fy, this was the derivative, and at y this was the derivative. So the angle that you are considering is this, okay. So this guy, this is the derivative fy, and this is the derivative of f1y, and this is, so this is like f1 prime y tangent, and this is like f2 prime y tangent, and what we are supposed to do is the interval between them, okay. So interval between them, this is the kind of like the negative is this one, and then the positive is this one, so I will take this, okay. You take this or you take this, it's the same thing. So this will be defined to be the subgradient, which is the interval of this, okay. So this is for max functions, okay, for max specifically. So I think I already defined, but maybe not precisely. So a vector G in Rn, okay, in Rn now, okay, so let vector G in Rn is called a subgradient at point y if for all x in domain of f, the same thing, right? Okay, what we said, f x is greater than or equal to f y plus g y minus x. So g will be defined to be subgradient when fx greater than fy plus g y minus x, okay, and the collection of all those g is called subdifferential. So that's another definition. So set of all subgradients at y denoted by del fy is called subgradient, or subdifferential, I mean, is called subdifferential. F at y. So subdifferential is a set, subgradient is one vector, okay, because we collect all the subgradients, right, then we call it a subdifferential. So obviously if f is differentiable, then subdifferential of f at any point y is the set that only contains grad f y. There is a singleton value there, obviously, and if it happens the other way also, the subdifferential happens to be singleton, then it's necessarily the gradient, okay, the usual gradient, okay, not the subgradient but the usual gradient. So if the subdifferential set happens to be just one singleton vector g, then g must be grad f at y x, okay, then g must be the gradient. So I have already given an example of fx is mod x, then in that case obviously the function is this, and then the subdifferential defined is, so for x less than 1 is minus 1, so basically it's minus 1, it goes here, and then plus 1 for here, and then it takes all the values between this also. At 0 it's between minus 1 and 1, and for less than 0 it takes minus 1, okay, and greater than 0 it's plus 1. Now let us look into some calculus rule, like if I take function fx plus gx, then the derivative of fx plus gx is derivative of fx plus derivative of gx. So does this apply here also? Subgradient of sum of a function, is it sum of the subgradients? Okay, so these are the calculus rules we say, okay. So what are the things you can inherit from the usual gradients cases, okay. So before that, yeah, so let us recall a little bit about what we know. So recall basic calculus. So addition was fine, right? So grad of f plus k, so gradient of a sum of a function is sum of the gradients. So this is grad f x plus grad kx. So this is something we know. So gradient is a linear operator, that's what we know. Gradient of a sum is sum of the gradients, and scaling also we know. So grad of alpha of f x is alpha of grad of fx. So this is something we know, and we also know chain rule holds in a usual calculus, right? So chain rule. So by chain rule, we need two functions, right, for chain rule. So let us do that here, and then we will see does similar things also work for subdifferentials. Okay, so then let us recall chain rule. So chain rule we have Rn to Rm, and we have K from Rm to Rp. Since it's a chain, this M and M should match. And okay, there is yeah, we need the last one, which is going from N to P, right? So then H will be N to P, Rn to Rp. So these are the functions given, and we define a composition of a function here. So let us say Hx is K composed with F. So that makes sense. So F takes N to M, and then K will carry over from M to P. Okay. So K composed with F. Okay. So sometimes we write this as K of Fx, K of F of x. Okay. And then we would like to apply a chain rule here. Okay. So if we apply chain rule, then the if we have to take a derivative with respect to x, then we see that it's a composition of this. So first we take derivative of K with Fx, and then derivative of Fx with x. Okay. That's the chain rule. So if we have to do dHx, so let us say this is the notation for the derivative, then we have d of K of Fx, and then d of Fx. Okay. So the chain rule says that if I have a composition K of f of x, then first I should take derivative of K as a function of Fx. So it's like d of K with respect to Fx. So d of K with Fx seen as a function of K, seen as a function of f, and then derivative of f by implicit assumption that it's with x, because f only is a function of x, so naturally it will be a. So this is the chain rule we know. Okay. So the question is whether similar things carry over. Let us see if we have similar calculus for subdifferential. So let us see scaling and addition first. Okay. And then obviously chain rule is a very tricky one. So let us see scaling. And so scaling, so if alpha greater than 0, alpha greater than 0, and what we are asking for is subdifferential of scaled function f. Okay. So if it was usual derivative, then alpha just comes out and we have f prime x, but in this case does it hold again? Okay. So if I scale, then how does the derivative look like, right? So this is indeed okay in this case. So I can indeed take out alpha and times. So basically I scale because we know that subdifferential is essentially a set. If it's not a set, it's a unique derivative. So that's the basic case. But if it is a set, then what's saying is that taking subdifferential of a scaled function is same as like scaling the subdifferential set computed at x. Okay. So this is like okay, this is a relief that okay, nothing much changed here. So this is alpha g, and g is in del of x. Okay, so basically I scale all the elements in the subdifferential, so that will work. Scaling is fine, and it turns out even addition is okay. Addition, so subdifferential of the sum, subdifferential of the f plus k at x is subdifferential of f at x plus subdifferential of k at x. So there was no problem. It seems like I can add two functions, and as a set, okay, remember all these guys are set, okay, as a set they are equal. Okay. So set of derivatives of the sum of a function is same as the element wise. Okay, is it element wise? Because this guy may have more bigger interval, this may be a smaller interval. Okay. So it's like I can add any of these combinations as a set. Okay. And they remain valid. Okay. So it would be interesting to see an example on this where actually they differ as an interval. Okay, it would be interesting to see, because like let us say we have a ReLU like this. So this is our f or something, and then we have some mod function also, which is like this. For this guy, the subdifferential at this is this, and for this guy the subdifferential is. So the sets may not be same, but it's interesting that we can sum them up as a set, and that will give me del f. Okay, it's nice. Like, I guess we can prove this to be very sure about that. Okay, so we can use the subdifferential definitions, and we can explicitly prove this to convince this. Okay, it's even written a star here, so it's like some proof is needed. So star means like a difficult one. Okay, so something, at least for us, let us remember this. We may not want to prove this right now, or maybe try this as an exercise maybe. So let us see chain rule. So yeah, chain rule, let us see whether chain rule holds, or is there any. It's almost time, right? It's almost time, so let us stop. Okay, 6:25 already. So we will see other things like chain rule, how it works. Okay then, thanks.